ternary diagram, first off, we know it's a mixture of methane, propane, and N-pentane. So we draw the ternary diagram. We put the methane at the top and pentane, which is the heaviest component, in the lower left side, and this becomes my propane. So we have methane, propane, and N-pentane. So if you're at point 1, then what we are going to do is we are going to look at every one of these laterals. So we are assuming we have a mixture of two components, okay? So the two components of C1 and C3, C1 and C5, and C3 and C5, to find what would be the state on every one of these laterals. And then when we identify the states of these mixture of two components on every one of these laterals, then we can connect them and then generate a mixture of three components, okay? So if I'm at point 1, so the point 1 is literally located at the N-pentane dew point. So I'm going to look at the C1 and C5 first, okay? So this is my C1 methane, and this is my C5 N-pentane. So point 1, so I'm in this lateral. I'm looking at this lateral, C1 and C5. So this is my methane, this is my N-pentane, and I know this is the locus of critical points between methane and N-pentane. So if the point that I'm looking for is outside this envelope, to the left, I know it's liquid. If it's outside to the right, I know it's gas. And if it's in between, I know I have both gas and liquid phase, okay? So in this case, point 1 is right at the N-pentane dew point line. And I know N-pentane dew point line is 100% gas, okay? On the methane, which is the bubble point line, I have liquid. And here, in pentane, I have gas. So in this lateral, what I have is all gas, because point 1 is located on the dew point line of a mixture of methane and N-pentane. What about the methane and propane? So if I'm looking at the methane and propane lateral, so this is methane, this is propane, this is the locus of critical points. Point 1 is definitely outside to the right-hand side of the envelope. So if it was in the left, it was liquid, in between liquid and liquid plus gas. So since it's in the right side of this envelope, I have all gas. So in between C1 and C3, I also have all gas. What about the C3 and C5? So this is propane and this is N-pentane, and this becomes the locus of critical point between the N-pentane and propane. Point 1 is again located on a dew point line of N-pentane, which is all gas. So I have gas here, I have gas here, I have gas here. So this whole envelope is gas. So the mixture of three components of C1, C3, and C5 that generate, no matter how much of which is combined, at all the conditions at this point is gas phase, okay? So moving forward, if I want to move to point 2, okay, let's say the pressure increased to point 2. So at point 2, I'm going to draw this again. So again, at the top, I have methane, I have N-pentane at the left bottom, and then I have the propane. If I look at between C1 and C5 lateral, between C1 and C5, point 2 is located inside the two-phase envelope. So this is my methane, this is my N-pentane, and this is the envelope. So point 2 is inside this big envelope. So definitely I will have two-phase region. I would have gas, liquid, and the two-phase region, depending on how much of C1 is mixed with how much of C5. Because this is my locus of the critical points. If I have more of a methane, then the envelope would be shift to the left, so this point could be only gas. If I have more of an N-pentane, the envelope will shift to the right, so this point could be in the liquid phase. Or if the envelope is somewhere in between, then I have both gas and liquid. So on this lateral, I should have gas phase, two-phase, and liquid phase. The gas phase should be top, close to the lightest component, and the liquid phase should be at the bottom, close to the heavier component. So on this lateral, I have the gas, two-phase, and the liquid phase. What about the methane and propane? Between methane and propane, point 2 is still outside this methane propane envelope and to the right, so it will be all gas. So on this lateral, I should have all gas. What about the propane and N-pentane? Again, in the propane and N-pentane, point 2 is located inside this propane and pentane envelope, so I should have gas phase, liquid plus gas, and the liquid phase. Again, the gas phase closest to the lightest component and the liquid phase closest to the heavier component. So on this lateral, I should have gas, liquid plus gas, liquid. On this lateral, I should have gas, liquid plus gas, liquid. And on this lateral, I should have all gas. So if I put all these together, gas, liquid plus gas, liquid, liquid, liquid plus gas, gas, and all gas, then I can come up with the envelope, which looks like this. The proportionality of these lines really doesn't matter. The only thing that matters is you just need to show there is a gas, there is a two-phase, and there is a liquid phase on this lateral. There is a liquid phase, two-phase, and gas phase on this lateral, and there is only gas phase on the other one. The size of these depends on exactly where these points are located. And since these are just the schematics, so we are not really worried about that. So if we move the pressure up to point 3, again, if I go to the point 3, if I'm looking between methane and N-pentane, point 3 is still inside the envelope, so still I should have gas, two-phase, and liquid. If I look at the methane and propane, so methane and propane, still point 3 is at the propane, at the dew point line, so this should be still gas. If I look at the propane and N-pentane mixture, point 3 is right at the bubble point line, because the left line is a bubble point, the right line is a dew point line. If I'm looking at the propane and N-pentane, point 3 is on the bubble point line. If I'm looking at the methane and propane, this point is on the dew point line. So I have all gas here, all liquid here, and gas, liquid plus gas, and the liquid here. So if I put all this together, I will have gas, liquid plus gas, liquid, all liquid, and all gas. So this becomes my envelope. If I move to point 4, again, between methane and N-pentane, this will be gas, liquid plus gas, and liquid because it's inside the two-phase. Between methane and, this time between methane and propane, point 4, between methane and propane, point 4 is inside the two-phase. So I should have gas, liquid plus gas, and liquid on this lateral. And in the propane and N-pentane, point 4 is in the left side of the envelope, so it should be all liquid. Again, if I connect all liquid, gas, liquid plus gas, liquid, gas, liquid plus gas, liquid. So this becomes my envelope. If I move up to point 5, again, this was inside the methane and propane line, methane and N-pentane line, so I should have the gas, liquid plus gas, and liquid on this lateral. On this lateral, this point between methane and propane is right at the locus of critical point. So it's either gas or liquid depending on how much of which component is mixed. If I have more of a gas, this point is in the gas phase. If I have more of a liquid, this point is in the more of a propane, this point is in the liquid phase. So it's not inside the two phase, so it's either gas or liquid. So I should have only gas or liquid. So I don't have the two phase on this region. I know the gas should be at the top and the liquid should be at the bottom. Okay. And between the propane and N-pentane, again, 0.5 is in the left side and up there, so it's all liquid. And then if I move further up, now this point, again, inside the two-phase between methane and N-pentane, so gas, two-phase, liquid. To the left of the propane and N-pentane, it's all liquid here. And here, between the methane and propane, it's above the locus of critical point. So it's either gas or liquid, but we don't know where this is gonna change between the gas or liquid. So it's either gas or liquid, okay? So, but we don't know that separation point. So the envelope shrinks. Go to the 0.7, it shrinks more, and 0.8, basically everything turns to liquid. So this is the evolving figure from the low pressure to high pressure when the mixture of methane, propane, and N-pentanes are gonna mix at a constant temperature. So you should be able to draw the ternary diagram of these mixture at any pressure given at any point. So you need to go over all these, make sure you understand how to plot the ternary diagram, and that also is one of your closed-book questions or the quiz questions that you will have. Okay. So what is the application of this? This graph basically shows one of the applications that we have generally in the enhanced oil recovery techniques, right? We will have our reservoirs when we, let's say we have an oil reservoir. When we start this reservoir, producing the reservoir, with the initial power of the reservoir, we are going to have some primary production. So when we drill, the pressure in the reservoir is high. We apply low pressure in the bottom hole, so the pressure gradient starts producing oil. But as the reservoir pressure goes down, we need to do something to keep removing more. So generally, the primary recovery is around like 30%, you know, 20-30% recovery of oil reservoirs. But after that, when the pressure starts going down, we don't wait till the reservoir dies, But when the pressure goes down, we start doing the secondary recovery. In the secondary recovery, generally we do water flooding. We inject water from some wells to push oil to the other wells. We are using the water as a piston to push the oil through the wells. So this increase the production and this increase the recovery factor to, let's say, 40%, 50%. And then after that, we need to do some other stuff like what we call tertiary or enhanced oil recovery techniques. And in those techniques, if you have a heavy oil, we might be interested to inject CO2, because if you inject CO2, CO2 gets dissolved inside the oil and drops the viscosity of oil. Therefore, it makes the oil less viscous and the oil starts moving. So when you inject CO2, you want this CO2 to get dissolved inside the oil. You just don't want to have a gas phase CO2, because the CO2 as a gas, if you want to push the oil, you just use water. You don't use gas to push the oil, because gas is going to break through to the oil. So you want to inject CO2. What you want to make sure this CO2 is going to get dissolved inside the oil. So you just want it to have a single phase oil in the reservoir, not the two phase. And to know if that's going to happen or not, what we can do, we can plot the phase diagrams, the Turner diagram, in which we've picked the lightest component, which generally is methane at the top, and all the heavier components than the methane, which we have in the reservoir, we call it C2 plus. We put it down here, and we put the CO2 here. Initially, we don't have any CO2 in the reservoir, right? So our reservoir condition could be somewhere on this lateral. And then as we inject CO2, the amount of CO2 goes up. So the line that connects the initial point to the CO2 apex will shows how the amount of CO2 will increase and how we are moving in this ternary diagram. Okay. So as I said, this ternary diagram assumes the fixed temperature and pressure. So we don't expect to change the temperature of the reservoir as we inject CO2, but the pressure will change. But if we assume that as the same amount of the CO2, or as we injecting the CO2 and the pressure goes up, we are also producing from the reservoir, so the pressure goes down. So these two kind of balance each other to keep the pressure constant. This could be valid. If not, if the pressure is still changing, then we will have multi-contact, miscibility, and then the graphs would be different. But let's assume the pressure is fixed and the temperature is fixed. So if this is the condition, I know if I inject CO2 in this case, this line, the red line, passes through the two-phase region. So I know this in this condition, originally I had all liquid in the reservoir. I didn't have any gas. Okay. But if I inject CO2, I start going through the two-phase, which means my CO2 is not going to dissolve inside this oil. So I'm not going to have miscible CO2 flooding. The CO2 is going to just try to push the oil. So this is not going to work. So this is immiscible. However, if I had a mixture which was like down here, if I had more of a heavier component and less of a methane in our mixture, so the point was here, and I start injecting CO2, then this line, if I connect that to this point, if I have like 90%, only 10% C1 and 90% C2 plus, then this line wouldn't go through the two-phase. So then this becomes a miscible CO2, because the CO2 always stays in the liquid. So this basically brings some value for our reservoir, and this way we know if the process will be successful or not. So and here basically we see some actual phase diagrams from the reservoirs, but that was the major point of this lessons. You will have the homework assignments and quiz on this as well.